Just housekeeping items. My name is Brad Hoffman. I'm an emergency physician here at Excelsior Springs Hospital. I'm board certified in emergency medicine, and I have no conflicts of interest and no financial disclosures. We are going to be talking specifically about the messenger RNA vaccines. Our goals are behind me. This will be geared toward the layperson, and if I fail to make it layperson friendly, I need to know about that. If I were getting some sort of education from our maintenance department on electrical circuits and whatnot, I would want it to where I could understand it. So I don't want to waste your time, so make it worth all of our time. Let me know, speak right up. So we're going to talk about DNA and RNA and ribosomes. Do not worry, you do not have to have a degree in molecular or cell biology for this. We just need to lay a little foundation for how these things actually work. And once you understand some of the basics of it, I think you'll see that it's a really simple principle. It was just really difficult to hit the last step and make it work, but they have finally done it. So we're going to talk about this LNP. You see over my left shoulder is the lipid nanoparticle, which is what's made the whole thing work. MOA, mechanism of action. We're going to talk about antibodies and peptides, and don't worry about all the lingo and all the jargon. We're going to boil it down into some pretty simple terms. So the way this kind of started, I was really frustrated because there's all this information out there and everybody seemed to have an opinion and have a belief, and nobody really asked any questions until one day one of our respiratory therapists came down, and I thought it was just a fantastic intellectual exercise on her part, and the vulnerability and her willingness to be open and to listen. She came down and said, "Tell me about these vaccines. Can you just tell me how they work? Tell me why I should not worry about this." So I thought at that point, we've done so much as a medical community, but have we really sat down and discussed how this works and why it works? So I went looking for various means by which to present this, and I found this slide program, and it's by David Spock of the University of Washington and the Washington IDEA program, IDEA, the Infectious Disease Education and Assessment program. So I hope you'll find this helpful. We'll just kind of walk through it here. Some of this stuff will be real applicable. Most of it will be. Some of it really won't. This is just the housekeeping things on Dr. Spock and University of Washington. So first of all, DNA and RNA. And we're going to compartmentalize this and boil it down real quick. You don't have to worry about memorizing DNA and RNA. DNA, it's a double-stranded helix, and its function is to basically store, encode, and replicate the genetic information of the cell, the genetic information that makes us who we are, that makes the cell do what it does and produce what it produces. The RNA, the ribosomal RNA, it converts that code, the DNA in the nucleus, down in the control center of the cell. It replicates and creates a strand of RNA, and it sends it out from the nucleus into the cytoplasm, out into the periphery of the cell where these things happen. And the RNA converts this genetic code from the DNA. And there's just one basic difference other than the single strand between the DNA and the RNA, and that's that it has uracil instead of thymine, and that is not necessarily important to our discussion tonight. In the human cell, the flow of information goes from the control center in the nucleus, from the DNA. When it replicates, its transcription creates the RNA. Transcription creates the RNA, which is basically an order from the home office in the nucleus, sent out into the cytoplasm, and then translation takes place in the ribosome, which we'll get to in a minute, and the protein is created. So the order goes DNA transcribed to RNA, translated into protein, and that's what we're going on. That's what we're going to want to talk about tonight. The protein that is going to be created is going to be an antigen. Moving on, the ribosome. This is the factory. So if you don't want to memorize what a ribosome is, this is the factory. This is where it gets done. So in the nucleus, like we discussed, the DNA replicates, it's transcribed into RNA. The RNA is the order, the menu sent out into the cytoplasm where it finds the ribosome. And as you can tell here, it looks like you're just feeding a ticker tape into some sort of little factory. And as it goes through, the ribosome creates this polypeptide, which eventually becomes the protein which is produced. So here's kind of what it functionally looks like and the different types of RNA. This is one of the things we don't really need to go into very much, which is the types of RNA. We're interested in the messenger RNA, and it'll kind of come together here in a little bit. So from the nucleus, from the control center, from the home office, whatever you want to call it, it creates a copy of itself, which is an order. It's a menu, if you will. It's sent out of the home office, out into the factory, into the ribosome. And the ribosome picks up this messenger RNA, and as it goes through, it's read, it's decoded, and this polypeptide is created. So Ford, we'll just use Ford Motor Company. The home office wants Ford Motor Company to produce this type of vehicle, so it sends out this order, and here's how to do it. It goes to the factory, and through the ribosome, through the factory, it pushes out an F-150 or whatever you happen. And I have no financial interest in Ford Motor Company. So now, put that in your pocket. Just remember, from the home office, we get an order, a menu. It goes to the factory pushes out the protein, the result. So we're going to change gears for a second. We're going to look at the severe adult respiratory syndrome coronavirus 2, the SARS-CoV-2, the novel coronavirus, whatever you want to call it. It is an encapsulated single-strand RNA enveloped virus. The spike protein is the major surface protein. So if you look and see those orange projections coming off of the envelope of the virus, these play a key role in binding to the host cell. So it finds a cell and binds with that. And if you look at the little box on the right, you'll see a close-up of the spike protein, and it's in what's called the receptor binding domain. This receptor binding domain is basically kind of like a spring-loaded little hook. When the spike protein contacts the cell, this little hook is projected out, and it attaches to the cell, and then the messenger RNA is injected. And the messenger RNA enters the host cell and uses the host cell factory, the host cell ribosomes, to create copies of itself and to make the cell not function appropriately, creates this cascade of events that we know as the infection of novel coronavirus. So the spike protein is the primary target of the host immune response. So our immune system sees this spike protein and basically says that's what we want to find, that's what we want to cover, that's what we want to protect ourselves from that spike protein. The spike protein is therefore the optimal immunologic target to use for these coronavirus vaccines. So the coronavirus vaccine, it's going to start coming together here in a second. So when we look at these vaccines, we're going to look at the, let me get that back up here a little bit so we can see the heading. There we are. And this is basically what the vaccine looks like on a microscopic level or submicroscopic level. It is a messenger RNA vaccine and is surrounded by what's called a lipid nanoparticle, the LNP, and this is the genius part. This is what has made this work. The messenger RNA is not necessarily very new technology. This has been investigated for a long time, but if it just injected directly into a person, it's recognized as a foreign protein and it's very quickly degraded. So somehow this has to be cloaked. It has to be hidden and disguised from our immune system so the protein's not degraded so that it can actually enter the cell. So the lipid nanoparticle, it's proprietary information, so it's not completely public as far as how it is, of what proportions it's composed. But long and short is, it's a phospholipid wall, And it's got these little polyethylene glycol projections on it. And the lipid nanoparticle, like we discussed, it protects the messenger RNA from being degraded and destroyed by the body when it's injected. And it facilitates the cellular uptake of the messenger RNA using the polyethylene glycol projections on it. So you can see the messenger RNA that's been engineered is inside the lipid nanoparticle. So moving on. It's just a little more simplified version, same basic headings there. This is, when you think of what's being injected as far as the vaccine goes, you can put this picture in your mind. It's basically this little fat globule with these polyethylene glycol projections on it, and it's got the messenger RNA in it. So it is injected intramuscularly, very small volume. The Moderna is 0.5 milliliter. It's given at 28-day intervals, 2 injections. The Pfizer vaccine is 0.3 milliliter, and it's given 21-day intervals. So it's injected here. It finds a little white blood cell or some cell that's what we call the APC, the antigen-presenting cell, goes to the lymph nodes where the immune system really kind of takes over and creates this impressive immunogenic response. Now, don't be intimidated by this slide. This is pretty busy, but I'm hoping it will make good sense. If you look down here at the bottom of the slide, you'll see the nucleus. This is the control center we were talking about, and this is where the DNA and all the cellular function process information is stored and coded and replicated. And then the messenger RNA, once it's transcribed, is sent out as the order, the menu, what have you, and it goes to, right here we've got the endoplasmic reticulum, which is where the ribosome, where the factory is. So it finds the factory and it puts out its product. So the difference here is that we're not using the nucleus. We're not putting DNA or RNA or anything in the nucleus. We're not changing the genetic information of the cell. This is coming from without. So this is what's been injected. This is the lipid nanoparticle, and it's got the messenger RNA in it. These little polyethylene glycol projections attach to the cell wall. It fuses, and now the messenger RNA comes in. And now it does the same thing that we would have liked for it to done through the nucleus. We're simply taking this item that we desire, we're putting the menu, the instructions in the cytoplasm, bypassing the nucleus, putting the instructions into the factory. We're basically going to Ford Motor Company and saying, hey, you're making a great, and I'm using Ford because they're right here local. So, well, I guess GM is too. Oh, you can send your letters later to me, care of the hospital. So we're basically putting this messenger RNA into the cell, and we're saying, hey, we're going to use your factory to create something that you haven't yet seen. So we're using your 3D printer, or we're using your assembly line to create these antigens. So we are basically creating identical copies of the spike protein. Once that's produced, it goes through the Golgi apparatus in the cell, and it's packaged in these little encapsulations, and then they're presented on the surface of the cell. So we have identical copies of the spike protein being presented on the surface of the cell, the antigen-presenting cell. These are also processed into what are little peptides presented on the surface of the cell as well. Now, why is that important? Because we have two different types of immunity. We have cellular immunity and humoral immunity. Don't worry about the terms. I'll just tell you what it is, and it should be hopefully pretty clear. So far, and this next slide is simply giving Pfizer and Moderna equal time. They're identical slides. One says Pfizer, one says Moderna. I'm not sure why they do that, but they do. So we have taken a piece of messenger RNA with the menu, the code that we want to build. We've injected it in a protective encapsulation, presented it to a cell, used its machinery to create antigens, the spike protein, as well as these little peptides. So these little peptides basically tell these CD8 T cells, hey, if you see another cell running around with these peptides on it, recognize that, kill that cell, because it's been hijacked and this machinery is being used to create coronavirus and make us sick. So if you see a cell with that on it, that identifies it as infected, go kill it. Now the B cells, they see the spike protein itself. And that makes the B cell produce, over here to the right, these little antibodies. These are kind of like gloves that cover the spike protein. So if the B cell sees something floating around, hey, those are spike proteins, that identifies the coronavirus, and it goes and puts these little covers, for lack of a better term, over the spike protein so that the spike protein cannot bind with your pulmonary epithelial cell and make you sick, or whatever type of cell it happens to choose. So that's the way it works. And when we look at these, this is, you don't need to worry about this too much, but these CD4 helper cells, T cells help the cytotoxic T cells activate, help the B cells activate to create the antibodies. And then for potential infections down the road, we have what are called memory T cells, memory B cells. So if we have an initial period where we're not exposed and we're not just actively creating a whole bunch of antibodies and cytotoxic T cell response, and we suddenly get infected, we suddenly get exposed, then these memory T cells and B cells basically make the factory crank out more and more and more. So that's kind of how we play catch up, or don't have to play catch up is probably a better phrase. So just going back over the narrative here, the activation of these cytotoxic CD8 cells that can destroy cells infected with the coronavirus, and then we have activation of the CD4 T cells that augment, like we said, help the CD8 T cells as well as the B cells respond, and then the memory cells, which help them be ready for actual infection. So there's what we've kind of been through. This is more for the distributors and the administrators of the vaccine, but that's basically it in a nutshell. So we bypass the nucleus, so we don't have any interference with our DNA. So it does not change our DNA because it does not go into the nucleus where the DNA is housed. And we're basically sending in a template using the machinery to create the antibodies, bypassing the nucleus. So we create this B cell and T cell response, so we can recognize infected cells to kill those cells, and then we recognize the virus itself based on its spike protein and go to work on the actual virus itself. So the goal of the vaccine, there's a lot of talk right now about breakthrough infections, and I don't like that term, but we'll use it anyway because everybody's familiar with it. The goal of these messenger RNA vaccines is primarily to avoid hospitalization and death. They are very good about preventing infection. There's no question about it. If we have a flu season where the flu shot gets 60-70% efficacy, we think we've hit it out of the park. This is far, far beyond anything that I ever dreamed we would see with an immunization. So the goal, keep in mind, if you hear breakthrough infections, oh, it doesn't work, oh, this, people are still getting infected. Well, to an extent that may be true, but when you look at it statistically, they are not being hospitalized and they are not dying for the most part. Are there exceptions? Absolutely, but functionally, statistically, this vaccine is working remarkably well. When we make our decisions, we worry about whether or not we have enough information. Well, to make an appropriate decision, we don't necessarily need enough information, we need the right information. So we have to ask ourselves, how do I, and this is a great question, how do I decide what's right? How do I decide who to trust? Well, this is just my way of thinking about it, but to me it makes sense. First, I ask myself a fundamental question: does this sound reasonable? Second, is it well documented? Is it in a source that I trust, or is it in Uncle Eddie's blog, or somebody just saying something. So is it reasonable? Yes. Is it in a trusted source? Yes. Finally, is it verifiable? Is it backed up by other research? Or is this just one person's little flight into research? So those are 3 things to ask. Does it sound reasonable? Is it documented in a reliable source? And is that source backed up by other research? So we talked about the purpose of the vaccine. So when we look at it statistically, we talked about breakthrough. Breakthrough infections. Again, I don't like the term, but when we look at that, we're talking about breakthrough in about 1%. But here's where the numbers are really good. When we look at hospitalization and death, as of today, my reading says that there are about 11,000 hospitalization/death out of 171 million vaccines, which comes down to your odds of being hospitalized or dead, 0.006%. 6/1000ths of 1%. I like the odds. For a while, we were looking at 8 times less likelihood of infection, and we were looking at 25 times less likelihood of death, hospitalization. Now, this number is going down, and it should go down, because the more we immunize and the bigger cohort we have and the more testing we do, the more we are going to find these infections. Most of them will be asymptomatic or very mildly symptomatic. Now, we look at this number, 25 times less likely to be dead or in the hospital. This number is actually going up. Last I saw, we were at 29 times less likely. So these numbers are going to diverge, and that's expected, and it's already happening. This number has dropped quite a lot. I'm not going to stand here and tell you what it is because I don't really know on today. But it's expected. When we look at Iceland, a lot of people were throwing Iceland out. Well, look what's happening in Iceland. They've immunized all these people in Iceland, and now you've got all of these people that are infected. And, so the vaccine doesn't work. The vaccine, how does that work? They're still getting infected. And my response is, thank you for making my point. They have a robust testing system. They test people, of course they have a smaller population, but when you test more and vaccinate more, you will find more incidental infections. But they have like 1 hospitalization, like 0 deaths. I don't know, this is as of a week ago. So the Iceland argument is actually a fantastic argument about how wonderful these vaccines are and how well they work. The other thing, let me get rid of this for now. There are all kinds of things to tail off of this. So when we look at prevention, when we look at stopping the spread, we see every time we have an infection and we have a transmission, so we've given it to somebody else, when there's a transmission, that can lead to a mutation, which is a change in the genetic code, which gives us, after a few mutations, it gives us variants. And right now we're dealing with this Delta variant, and it's awful. When we get enough variants, we go through a lot of variants, then we start looking at, we have to change our vaccine. So if we get enough people immunized and get herd immunity, we stop the transmission, which means we stop the mutations, we stop the variants, and we got one vaccine we're getting by with. So the other thing, if we stop transmission, I understand everybody's freedoms and everybody's liberties. The problem is, it ain't just about me. It's about this person. She's 42 years old. She's a mother of two. She has chemotherapy because of breast cancer. What's that do? Makes you immune compromised. So we can vaccinate, but the whole point of chemotherapy or immunologic drugs that treat Crohn's disease or plaque psoriasis, the whole point is to decrease the immune response. So we can vaccinate them, but we are going to have still an inordinate amount of susceptibility. So if I get immunized and I can decrease, if I can make that number that we talked about 8 times less likely, which is, again, not a good number at this point, then my decision just made her chances a lot better. So let's talk just for a second. And here's another thing. I'll just tell you the things I don't like. I mean, there are things about this that are confusing, and there are things that I don't like that aren't necessarily real palatable, that aren't real solid, but I will tell you. So there's a factor that we call the R naught, and that's pronounced N-A-U-G-H-T, which, for those of you who are old enough to remember the Beverly Hillbillies, Jethro wanted to be a double naught spy, which was a 00, like a 007, so this O is naught, R naught value. I will tell you that the R naught value is very variable. It relies on all kinds of different conditions, and it's open to interpretation, but if you look at it as a sum total, we're seeing that the initial coronavirus had an R naught value of about 2.5, which means under these circumstances, in this frame of time, in this close contact with these many people, that somebody that's infected is going to give that to about 2.5 people. Now, when we look at the Alpha variant, we're looking at about 4 to 5. And then now with the Delta variant, we're looking at probably around 7. Some say maybe 9 to 9.5. I'm just going to tell you, don't take that to the bank. You can probably take this to the bank. I don't know about this. But if this is true, that leaves only one virus that we know of that is important to us that's more infectious, and that is measles. Not a big problem right now, not here, but kind of turned into a problem in California not long ago. So right up there with chicken pox, but I think I don't like being an extremist. So again, this is just a guideline. These aren't like hard factual numbers that we can go verify real easily. So that's the R naught value. Now, here's something that's real scary. It should be scary. I hate this, but it's true. It's scary. I'm terrible at doing these graphs, but we'll try. So when we look at somebody getting infected, let's call day 0 the time where you have the highest viral load. So we'll say highest viral load is day 0. So this is where you are the most contagious. You're shedding the most, you have the most, that's where you're most contagious. Here's the problem. Guess where you're symptomatic? You're symptomatic right there, about day 2. So you're infected somewhere around here. You're building up some antibodies trying to get out here to where you're not symptomatic anymore, but right here, feeling fine, but out there spreading it. So that's the scary part. So if I have the option, if I can choose between starting here, building up these antibodies over the course of time, I have to get from my time of infection to my time of resolution, hopefully resolution. If I am immunized, I'd love to start my antibody response somewhere right here, because this is a pretty rough time to get through right here. I'd love to start right there and get to there by basically starting here, or even not being symptomatic. So, terrible diagram, but hopefully gets the point across. You're contagious about 2 days before you're symptomatic. So that's why contact tracing is very important, which we've pretty much failed at doing. Oh, yes. Our lab director, Frank Gonzalez, has been involved in this research. And this is really fascinating because people ask, well, if I get the coronavirus, I've got antibodies, right? Yes, you do. Absolutely. Well, aren't my antibodies that I have organically made against this novel infection better and more? The answer is no. So here we have infection. Here we have vaccine. And here we have both. So when we look at it graphically, basically see something like this. Infected? Yep, I got some antibodies. Good deal. I get vaccinated because of the immunogenicity of the way the vaccine is engineered. I have a much more robust immune response. And if I have had both, I get even a little bit more. Do not take that as an endorsement of going out and getting infected, but that's the way it works. We've engineered it. I say we, I'm not nearly that smart. It has been engineered to create a much more robust antibody response than being infected. So, I'm young, I'm healthy, I'm bulletproof, I probably won't get it. Well, if you are not immunized, statistically, the chances of you getting coronavirus at some point, 100%. When we look at it statistically, the way the Delta variant is going through, your chances of getting are 100%. We need at least, and these numbers are a little soft too, I'm just going to tell you, we need between 80 and 90% immunization for what we call herd immunity. I'm not real crazy about that term either, but, and I got to be a realist, told you to be honest with you, ain't going to happen. I hope it does. I hope I'm wrong, but it's just not going to happen. So that's what we need for herd immunity. Which brings us to, and I won't spend a lot of your time with this because it's not why we're here. It brings us to non-pharmaceutical interventions such as masking and distancing. So these are temporizing measures. These are temporizing. They do not get us to herd immunity. So, side effects. You've heard stories. I've heard from people, a lot of people. Oh, I got the vaccine, and I just felt terrible for a couple of days. My joints hurt, my muscles hurt. I just felt terrible. Just felt terrible. Congratulations, your bone marrow works. You've got a good immune system. It's doing what it's supposed to do. If you didn't have the symptoms, I didn't have any symptoms. But if you don't have the symptoms, don't worry about it. It's still going to do what it does because we saw the mechanism. So, yeah, those symptoms. But if I'm looking at a huge decrease in my risk of becoming infected, and even more so, the whole purpose that I am at about a 0.006% chance of being hospitalized or dead, I'll take that every time. I'll live the rest of my life that way if I have to, but that's just me. So your odds are extremely good getting this vaccine as far as not getting the coronavirus and as far as not suffering a poor outcome from it. Side effects we discussed. You can also, we've also seen, and mainly, and this is not necessarily with, there have been reports, but mainly with the J&J, which is not a messenger RNA vaccine, we have seen myocarditis, which is an inflammatory condition. We all seen pericarditis. These are inflammatory conditions of the heart. The heart muscle itself can become somewhat inflamed, give you a little chest pain. The pericarditis, the sac around the heart, same kind of deal. Generally self-limited, minor, no definitive therapy. If you get a virus, let's say you just get the common cold, or you get the flu, or you get, there's not a virus, but so you get strep throat, you can get myocarditis. And when you have an immune response, the inflammatory response, you can get myocarditis. I will tell you, full disclosure, there was a case today or yesterday in New Zealand. Someone died with myocarditis. I'm sure that'll hit the news, but keep going back to that 0.006%. It's still statistically doing everything and more than we ever dreamed this would do. Myths. We talked about altering the DNA. It will not alter your DNA because it doesn't go to your DNA. It never enters the nucleus of the cell. Your DNA is completely safe right there in its home office, giving orders. And once its machinery is not being used to create antibodies, it'll go back to doing what it's supposed to do. It does not affect your fertility. It does not cause miscarriages. It's definitive. You saw the mechanism. It does not go do things to your reproductive system. It will not turn you into a magnet. If we injected that volume of elemental iron in you, you still would not, the dilution would be to where you would never become magnetized. And if you were magnetized, your blood would cease to flow, your electrical functions would cease, and you would just die immediately. You will not become a magnet. They aren't tracking you. I can tell you I don't think I'm that important. If they want to track me, they can use my cell phone. The smallest microphone known, I believe, is about the size of the eyelet, the little hole in the end of a fish hook. So as far as tracking you, no, this is just a little liquid suspension with the LNP and the RNA in it. We don't see polio anymore. When polio came out, everybody went flocking to get the polio vaccine, and we've pretty much eradicated polio. Same with smallpox. This is such an inordinate advance over anything like that we've ever dreamed. I wholeheartedly endorse this. So, any other myths? I can't think of them.
I did have somebody that asked if there was aborted fetal cells last time in the vaccine.
Right. Yeah, there are no aborted fetal cells in the vaccine. Going back historically to when the messenger RNA was engineered, I have not gone back and independently verified this. I have heard, and I want that to be out there, I have heard that voluntarily aborted fetuses from the 1970s tissue was used for messenger RNA. I don't know. That's something, like I say, it does not affect the mechanism. I understand the ethical and moral concerns. That may be something you have to go look up. I have not personally looked into that.
A lot of people are saying that masks, because the kids have to wear them all day, there's all this bacteria, and there's carbon dioxide being trapped and all those types of things. So do you have any, as far as masking goes, do you have any,
Yeah, as far as masking goes, if you want to culture what's on the inside of a 5-year-old's nose, probably should be sitting down when you get that result back. It's not, I can't speak to what's actually cultured out of the inside of a mask. I would like to think that they would be washed from time to time. That's just my own personal hygiene recommendation. But masking, yes, the American Chemical Society did a very nice study showing the efficiency of cloth masks. The very poorly woven ones with a very low thread count, looking at about 80 threads per inch, real variable, about 5 to 55% efficiency, not great, but still significant. When we're looking at a thread count of about 600 threads per inch, we're talking around 80%, and it protects those around you more than it protects you. So it's to protect other people. And then when you incorporate, like if you've got 2 layers and there's a pocket between it, I mean, this is all I ever wear, so I'm not sure what all's out there. But if you put in a piece of silk or if you put in a piece of chiffon, you get electrostatic filtration. And these studies were done using droplets. And again, that's a great point, and it takes me to another point. This is not virus floating around in the air. I mean, yeah, it is, but the virus is in a respiratory droplet. It's in a little drop of water. So we have to filter the water droplet. We're not filtering virus. So if you go look and see, oh, how big's a virus? Oh my gosh, nothing will ever filter that. Well, you're right, but it's arresting the airborne droplet that comes out. So if we're looking at droplet size, and I'm sorry I'm getting too deep on this, if we look at droplet size between about 5 micrometers and 10 micrometers, those larger droplets just go to the ground or the table or somewhere, and within a little bit of time they're rendered inert. It's the 3 micrometers. It's the, I hope I didn't say micrograms earlier, 3 micrometers, 5 micrometers that are the smaller droplets that are pushed out into the atmosphere, out into other people. So these masks, the American Chemical Society studied these at 300 nanometers, which is 3/10 of 1 micrometer. And they found these results. About 80% efficient with 600 thread count. Around 90% efficient if the pocket has some chiffon or some silk in it for electrostatic filtration. It becomes, if it's well-fitting, it rivals an N95. It's not quite as good, but it's in the ballpark. So if you've got that, you're in good shape. And when you look at that with the chiffon in it, now we're talking down to about, if I remember correctly, 10 nanometers. So 1/3 of what they looked at with the other mask. This is like 10 nanometers up to about 3 micrometers. So much, much smaller with this really impressive effect. So NPI, non-pharmaceutical intervention, yeah, I opened the door on that, and that's kind of what you're looking at with the mask. These are endorsed by the American Society for Microbiology. The studies are strong there, as well as with the American Chemical Society. American Academy of Pediatrics has come out and with a robust endorsement of masking kids going back to school. They want them back in school. The American Academy of Pediatrics recognizes the toll that it takes. But there has never been one objective study showing any physiologic decompensation or any kind of physiologic stress on a child playing with a mask on or an adult exercising. It does not retain carbon dioxide. It lets oxygen in. These are gases. These are not particulate. These are gases. So that's the story on that's probably more than you ever wanted to hear on masks. So, yeah.
Sometimes you hear that people are saying the vaccine must not work because they're saying to still wear a mask even though you've been vaccinated. So can you kind of explain that?
Oh, sure, absolutely. We said, and this number is falling, but this is the only number I have right now. We said that you're 8 times less likely to become infected, which means with this number dropping, I still have potential to become infected. And if I become infected, whether I'm symptomatic or asymptomatic, I can potentially still potentially transmit it. So personally, I love this number, even if this number is not accurate, even if it's a lot lower, but I believe in giving myself every possible opportunity, not just to become not infected, but to not affect that person. I don't want to take a chance on going to give that 42-year-old female on chemotherapy for breast cancer or something. That's why I wear a mask even though I'm immunized. So, great question.
Another myth that was given last time is the vaccine the live virus being injected into?
Vaccine is not the live virus. It's not even a dead virus or a damaged virus. When we talk about flu shots, also I believe the Johnson & Johnson vaccine, yes, those are either live attenuated or killed virus. These, as you saw with our mechanism of action, there is no virus attached at all. And when these antibodies are presented on the antigen-presenting cell, they're in a form that's called a pre-fusion stabilized mode. It's so, remember that we talked about that little spring-loaded hook that comes out and attaches into the cell? When these antigens are presented to the antibodies, they are in a form that spring-loaded hook is deactivated. It's a pre-fusion stabilized, so it's not in a fusion mode. It's stabilized, so it will not do that. And yes, there is no virus injected into you. Only the menu to create the antigen to present it on the cell. So, great question.
This isn't about the vaccine, but we do sometimes hear people say, well, I've already had COVID, so since I've already had it, I can't get COVID again.
Great question. If you had coronavirus, let's say you had this back in, let's say you had it back in April of 2020, and I'm just making up dates. So I had it then, I didn't, but let's say you had it then, your odds, if I can remember how to use the marker, your odds are actually twice being reinfected. So yes, you absolutely can. Remember we talked about the here's how much antibody you have if you've been infected, here's how much if you're immunized, here's how much if it's both. So yeah, and there's talk about boosters. I'm not really prepared to talk too much about boosters, but it was going to be 8 months. Seeing a lot of studies out of Israel, seeing a lot of anecdotal information and some studies coming out that, hey, 6 months might be a little more what we want. But we don't want to just go out and get a booster at 3 or 4 months. We're going to get a more robust, at least preliminary studies have shown, we're going to get a more robust booster immune response if our immunity kind of wanes a little bit. We're not going to lose that immunity. We're still going to have those CD4 helper or the T cell and B cell memory cells, but if we start to wane, we're not going to wane to the point that we're uncovered, but if we wane to a point and then get to booster, then we spike back up again with a more robust response.
And then the other thing is we do also hear a lot about children, and that children, are not at risk at getting very sick with COVID. How has that changed?
Oh, golly. That's changed in the sense that I had to hold a patient over here in our emergency department for about 3 hours waiting for a bed at Children's Mercy. I have a cousin who's an oncologist over there. He said they have never seen volume like that. They will not close their ER, but it is a dire situation. And we've got it easy here. I mean, you look down in the southeast, it's tragic. These kids are getting it. They're getting sick. there was a school district, I think, in Texas that was open all of 3 days, and they had 730-some quarantines. There have been whole school districts that are closed because of exposure. But yeah, this Delta variant is a completely different ballgame, and these kids are getting sick, and these ICUs are filling up. Some of them are going on ventilators. I don't want to paint a whole doom and gloom. I don't want to give you false information. But yes, it's difficult. It is difficult. I had a 3-month-old that had coronavirus, was doing fine, but we look at with these kids, once their inflammatory cascade starts, they can get what's called multi-organ system inflammatory disease in children, or MISC. Multi-organ inflammatory syndrome in children, MISC. And it resembles a lot of different infectious and inflammatory conditions that are really extremely serious in kids. Now, is that the rule? No, absolutely not. It's more the exception than the rule, but it's the rule if it's my kid. And then I think last time we also had a question, why do they not vaccinate kids under the age of 12? Well, it's simply because the studies have not been done adequately on kids under the age of 12, and that goes back to ethical concerns. If these studies turn out that they're killing a bunch of people, we can't be killing a bunch of kids. So we've seen exactly the opposite. I know Dr. Strickland he's been very open about how by hook and crook he's tried to get his 6-month-old involved in clinical trials. If I had a 4-year-old or any age, knowing how this works and knowing how safe it is, I would sign him up regardless of age in a heartbeat. I would not hesitate if this were my own kid.
Because initially it was older people, right? Is why they
Yeah.
didn't do a
Yeah.
group of children
Yeah.
in the study.
Yeah,
right?
you can say it was older people, but we're probably truer to the truth is it was older people having the poor outcomes. So as far as susceptibility, yeah, people say, oh, the kids aren't getting it. Well, we just had pretty terrible testing. I think in retrospect, the kids probably did have it. They just tolerated it better until we got to this Delta variant. So, yeah. And then, it seemed like there's something else I was going to add. But, yeah, that's, I know. There was a deal on the last time. Somebody said, well, how has this gone through so fast? Usually these take years and years to evaluate from the FDA. So how do we really trust this because it's gone through so quickly? The reason it's gone through so quickly is because we have amassed more data in a shorter period of time, I am convinced, than any other medical data in this span of time in human history. There has been so much work, so much research by so many organizations to compile the data that we have what we need to get to the point where we are in improving this. And it seemed like it took forever, but it didn't. It was warp speed. It was really fast. But it was simply because a lot of hardworking people did their work and compiled the data and established that it's safe, it's effective, and that's where we are.
So I've got 2 questions. These might be too much in-depth to get into, but so you mentioned like if you've had the original COVID virus, you're 2 times more likely to become infected. How does that work?
I don't know. That's just the number I read. I'm not sure how that works. If it's a matter of that the Delta variant, you should have some antibody, but I don't know if that may be reflective of several different factors. It may reflect that you're not doing the non-pharmaceutical interventions, that you're placing yourself at higher risk, that that you're higher exposure. I don't know, but I'm not. I don't have a great answer for that. I can just kind of tell you the number.
And then, so you said it's like what was it, 0.0006%. What is the likelihood? I'm thinking of all my people I know who are always like criticizing things. The chances of dying or being hospitalized if you haven't gotten the vaccine.
I honestly don't know, but it depends a lot on several things as far as your odds: age, gender, comorbidities such as diabetes, hypertension, coronary artery disease, and the list goes on. Other things, this coronavirus It can kill younger people because it makes us hypercoagulable. It makes our blood a little too thick. It makes it more likely to clot. So some of these people actually may tolerate it pretty well. They form a clot that goes to their lung and kills them. Or they form a clot that goes to a coronary artery, they have a heart attack and they die. So a lot of it also, another risk factor is weight. So there's all kinds of factors that go into it. So what are your odds across the board of dying from it? I'm not really sure. And it changes. It has changed. I mean, it was like, 1 point something percent at one point. And honestly, I have not looked recently enough to give you good numbers on that. I apologize.
And is it a true statement with this Delta variant, we are seeing younger people more negatively affected?
Oh, no question about it. No question. I mean, we're seeing young, healthy people, 40s, 50s. I was saying, and the last time we talked, it'll be 2 weeks ago this coming Wednesday. I saw one coronavirus, in addition to the other patients in the ER, we saw one coronavirus patient per hour, and they represented every decade of life through the 7th decade. The youngest was 3 months, a couple of 14-year-olds, and then 20s, 30s, 40s, 50s. The oldest one was 65. One was critically ill, actually. And thanks to our great inpatient management team, Dr. Slack and the nurses, in the ER, we got her oxygen saturation back up, and we stabilized her to the point where we kept her here because there were no ICU beds anywhere. We could not get an ICU bed for that patient. So we would have had to hold her in our ER, which emergency departments do a great job. That's why I do it. But emergency department is not a substitute for an intensive care unit. But we were actually able to stabilize her to the point her oxygen saturation came up, did not have to intubate, and as far as I know, the patient did fine. But we were at that point really, really nervous because if this patient decompensated any further, it would have led to intubation, ventilator, and no hospital other than here, which I'd like to think we could handle that, but that's not our job. That's not what we do necessarily. But
you hit all the myths, I think. So
well,
great job.
I appreciate that. Thank you for all who are in attendance, and we hope that we
appreciate it very much. It was very informative.
Anytime.
It's all lots and lots to think about.
Great.
I do have a question.
All right,
Go
we got
ahead.
a question. Go ahead.
Yeah. It's Mallory. So I've been reading along on the Delta, and I found some information about a subvariant that's forming, the Delta Plus, and I guess it's starting to affect the spike protein. So I was just kind of curious what kind of problems that's going to cause with us who've been vaccinated. Is it going to increase our risk of getting the Delta variant?
I have not actually heard about the Delta Plus, so you're ahead of me there. It does fall completely in line with transmission leads to mutation, which leads to variant, which leads to new vaccine. So if there is a mutation and it's created some deviation of the Delta variant, that would be a logical stepwise progression. And I don't think I can speak intelligently as to probably a lot of things, but to that, I don't really have a great opinion, and I certainly don't have any kind of objective or evidence-based knowledge. So sorry about that. I'll have to look into it.
My guess is that scientists are probably already working as hard as they did on this first vaccine, looking at ways that they can be quick and responsive to all these variants.
Oh, I'm sure, and that's a good point too, because it used to take months and months to map the human genome. Now they can do it in 3 days. So I think they have what they probably need. The question is, what does it look like? How do we sequence it? How soon can we roll it out? And it's really, really scary because in my opinion, there will probably be a time where it's not covered, where, this is now in India, or this is now in wherever, because India is kind of the canary in the coal mine. What happens in India, kind of poverty-stricken, poor resources. Now we're seeing, let's say the Delta Plus, or let's say the whatever variant. Now we got a problem. We got to reformulate vaccine. Now, how long does it take? I don't know. But people will be waiting, and And it's just going to create a cascade effect unless people get vaccinated. This is the only way to immunity. This is the only way to arrest it. And it doesn't get arrested by ignoring. Once we need another vaccine, I don't know where that slippery slope stops. I don't know if it ends with a whole bunch of people that are not vaccinated leaving only the vaccinated. I mean, that's an extreme, but that's one path to herd immunity, is when a certain cohort is no longer here.
Very good. Any other questions from our Zoom attendees? All right, well, thank you very much.
Thank you all.
We were able
Thanks.
to